Morning then, guys. Tim back again. Right, I'm going to do a sequence of videos for UA2 students, and I'm going to do Proton NMR Spectroscopy, which is the last really important topic. It's going to take me a few lessons because it's quite tricky, and it's a sequence that you have to learn how to do to get good at the basics, then build up to the sort of questions they ask you in the exam. So it's not going to be something I can teach straight away in one lesson. So we'll see how that goes, and I'll see. I don't want to make the videos too long because they take ages to upload, hours and hours. So I'll try and keep them as small as I can. And there will be a sequence going through and that really is the last big topic. So once I've got these lessons out of the way on spectroscopy, look at them. There will be packs sent to help you anyway soon enough. Look at them, do them, understand the technique properly and fully, and get yourself up to speed on it. After that, I've got a bit of mopping up to do on things like chromatography, gas chromatography and thin layer chromatography, which are very straightforward and easy. After that, I'm pretty much finished the specification. Okay, I can do some other stuff maybe to keep revisiting, but you'll have everything you need. You'll have completed the A-level chemistry course, and I think that's important. Okay, for me, that you've had it all. Okay, so enough yap from me. I better get started. I'm dreading doing this because it's a bit of there's a lot to it, but we'll give it a go. So hopefully you can see me. I'll just check. Yeah, looks all right, looks okay. Right, so title, I'm in the wrong colour already. Proton NMR Spectroscopy. Proton. Right, okay. This idea of proton. I don't know why they call it proton. People who are cleverer than me will be able to say that. What it's detecting is, it's detecting they call them protons, they're hydrogens. So carbon-13, which you will see that there are links to carbon-13, particularly in terms of the chemical shift in the environment and the idea of equivalence. It takes carbon-13 much further forward than that. But that's a good starting point for basic principles. Protons, as far as I'm concerned, are hydrogens in an organic molecule. Okay, and there's a lot more hydrogens in an organic molecule than there is carbons. So therefore this technique is more sophisticated and trickier to interpret. Okay, that's initially first thing to say. For one reason, we'll see the similarities, we'll see the differences. Okay, so first of all, this idea of proton just means the hydrogen. Okay, now there's a few things I want to get out of the way first. Right, you take your sample that you're going to do an NMR on and you dissolve it in a solvent. Now this again should make sense to you because you dissolve it in a solvent, and the solvent we've met before, CdCl3. I'll draw that out. That D, as you know, is deuterium, one of the isotopes of hydrogen. Okay, normal hydrogen, one proton, one electron. Deuterium, one proton, one neutron, one electron, and then there's tritium with two neutrons. Okay, either way, that will be picked up in NMR. That is what most hydrogen is. That will be picked up. That's what NMR responds to. Proton. That's as far as we're concerned. That's what they call a proton in Proton NMR, basically. Even though if that's a proton, if it loses an electron. Okay, but they call it Proton NMR. Okay, that will not be picked up. In other words, what I'm saying is the solvent is completely doesn't mess up, doesn't get involved, because that D will not be picked up. That deuterium will not be picked up. It's a totally inert solvent that doesn't interfere. Okay, deuterated chloromethane, it's called. Okay, so that's your first chemical. You've got to dissolve it up. Then you need something called an internal standard, and this is good. Okay, an internal standard, and again, I'm sure we've met this, is called TMS. Tetra methyl silane. Silane. TMS. Okay? What on earth is that? Silicon. Cool. Silanes are a bit like, because carbon can form these almost, incredibly long carbon bonds. That's the whole basis of organic chemistry, the ability to catenate, they call it, the ability for one carbon to join onto another, to join onto another. Silicon, being in the same group, and I don't know why, can also do this. So you can have a whole family called silanes, where silicons can join to each other. Nowhere near as effective or as big as carbon, but possible. Okay, so tetramethylsilane, by its very, is this. Now, this illustrates an important principle, both for carbon-13 NMR and for proton NMR. What I'm saying is, how many peaks are you going to get for this in carbon-13? Answer 1. Carbon-silicon, 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 carbon-silicon. They're all identical. Think of a line of symmetry that way and that way. Those are identical. Likewise, the protons. 3 there. Exactly the same as 3 there, exactly the same as 3 there, exactly the same as those 3 there. In other words, you are going to get 1 peak, and that is at the chemical shift of 0. Now, what that does is calibrate the machine. That gives you the 0 for your scale of chemical shifts that we'll come to shortly. But the idea of those being equivalent is quite useful. Okay, that's important. Now, we'll get rid of this, because the first thing I wanted to use to show you about how to interpret these, this is, I suppose, an introductory video, okay, is low resolution NMR, low resolution proton NMR, okay. Now, what's all this about? Well, low resolution, the things that produce the spectrum, the things that matter are this. Number 1, low resolution gives different chemical shifts for different environments. So you need to take into account chemical shift, which we're coming on to. Alright. Number 2. So low res will give you some idea of the environments of the in fact, not some idea, it tells you the environments of the protons, you will see. So that's one thing it does, even though it's low res. Okay. Number 2 is that's exactly the same as carbon-13. Okay. Number 2 is what's called the integration trace. That tells you how many protons there are in each environment, okay? And we'll be using that. That's quite important. That is an extra from carbon-13, which didn't tell you how many protons there were in that particular environment. So that is new. And finally, what low res will not show you is something called splitting. To give it its correct word, spin-spin coupling. And this is where it gets it very interesting. Okay, because the splitting, but you won't get, so you get that with low res, you get that with low res, you don't get that with low res. What I will do is when I move on to high res, we'll bring the splitting into the equation. Before I get into the splitting is where it gets tricky. The splitting is when the peaks in what's in low resolution, at high resolution, adjacent protons on adjacent carbons interfere with each other and split the peaks of the low resolution into smaller peaks that you can use to determine the structure of the molecule. And we should be looking at that, and that's the hardest part of proton NMR. The rest of it is not too bad at all. So we need to look at splitting patterns and what that tells us. But I don't want to do that at the moment because I want to stick to low resolution. But it's important to remember that low resolution doesn't give you less peaks. It simplifies it because there's no splitting. It doesn't give you less peaks. It looks like there's less peaks, but what it's doing is taking the same peaks at low res and high res, splitting those existing peaks into groups of peaks, not actually technically adding any extra peaks. So high res is taking low res further, but taking two vital principles further simultaneously. Okay, so we'll come to splitting a bit later. Right, okay, I think I want to look at chemical shift now, if I can. So I'll get rid of this. Okay, now you should have one of those lovely, lovely data sheets, which I seem to have lost already. If I put it here, bear with me guys, I think you should be able to see that if I can stop wobbling it. I think it's difficult to see on this, but I reckon. Carbon 13 we've had a look at. Those are the chemical shifts. Okay. Now, you'll get this obviously as you know in the exam. These are the environments for protons attached to carbons that are attached to other things. They have different environments. Looks weird at the first glance, but you should be able to suss that out when I've been through it. So I'm going to break this down. I get the data sheet out and refer to it while I break it down now on the board. Okay? Right. Right then, chemical shifts. This definitely needs a little bit of investigation. Delta is the abbreviation for chemical shift, and it's in parts per million of the units. Right, simple. If you look at that sheet that you should have in front of you, that data sheet, you'll see we'll go from the right to the left. So you'll see a scale that goes from 0 to 12 parts per million chemical shift. I'll show you it again. I hope you can see 0 to 12. We start here. For these are more common. Well, not necessarily, but that certainly is. And these perhaps, I wouldn't say they're less common, that depends. But you know, you get a lot of peaks in this area. So we start off on the right hand side and we moved gradually to the left hand side. That's the plan. Okay, right, so what do these mean? We start on the right hand side. I find this one quite tricky, so we have to be right with it. H. Shall I have a colour? Yeah, why not? Look at that. Yeah, go on. H. C-R. Biggie this. 0.5 to 2 chemical shift. Okay, that means a proton. When I do the examples, you'll soon see what I mean here. That means that is the chemical shift of protons attached to a carbon that attach to a methyl group or an alkyl group. I find this one the hardest of all. Basically, you might have a sequence like this. CH3, CH2, I don't know, O. Those protons there, I find, you know, are going to have a chemical shift between 0.5 and 2. This is misleading, I suppose, but those protons there will have that chemical shift. In other words, the protons that are in an ordinary hydrocarbon chain have chemical shifts within this area, so there's a lot of them, and they're very prone to splitting, which we'll deal with later. That looks misleading. These protons, they're attached to a carbon which is attached to an oxygen, so they are on a different chemical shift, which we'll come to shortly. But these three here are attached to a carbon that are attached to a carbon with H's on. Okay, they're part of a carbon chain. Okay, so they will have a chemical shift in that area. A nasty one really to start with, but we'll get the hang. Okay, now down the bottom end there's a benzene ring thing lurking. Okay, there. C H. Okay, what's that all about? Well, that one's a bit easier. So it says the chemical shift is 2 to 3.0. That is the chemical shift for protons attached to a carbon which is attached to a carbon in a benzene ring. Right? Attached to a carbon which is then attached to a carbon within a benzene ring. Classic sort of thing might be this. You've got a benzene ring, which we'll discuss later. I'm tilting this a bit. CH2 on there, then goes on. Those two protons will have a chemical shift in that environment. It's as simple as that. Okay, next. Let me come on to what I would call the slightly, don't know whether they're easier or what. C, double bond O, there. H is there. This one's okay. Again, this is a busy area, 2 to 3. There's quite a lot of weird stuff goes on in this area, so, you know, that one we'll see. That one we'll deal with. I wouldn't worry about it, it's no problem, it's dead easy. But the splitting might be a problem for you. This one, fairly clear, okay? This one, again, quite clear. This is the chemical shift for protons attached to a carbon which is attached to a double bond oxygen. So, you know what, I've cocked that. I knew I had, because they can only fit one on. See, deliberate mistake, just goes out to show you make all these notes and then they go wrong. That chemical shift is for protons attached to a carbon which is attached to a carbon with a C double bond O. You've got to sort of shift your brain a little bit to further down the line. Look at adjacent, look at things that are adjacent. You'll see what I mean later. So, looking at that, well, that opens up, there's all sorts of possibilities. Anything attached to that C there. So, we'll have a chemical shift in that environment. So maybe we'll have a methyl group there. They will have a chemical shift in that environment. Okay, maybe we have, get rid, 2 H's on it. Maybe there's a chain along here. Right, those 2 H's. Those 2 H's, and it carries on and does something else. Those 2 H's will have a chemical shift between 2 and 3 because they're attached to a carbon which is attached to a carbon which is attached to a carbon with C double bond O. Sounds confusing when you first see it, but that's quite big because that opens up esters, and esters are quite popular in NMR spectroscopy, and I'll be using esters quite a lot to show you how all this fits together. Then we've got a couple more which I want to squash on for you. H, C, N. Okay, so that is again 2 to 3. Okay, now that there is probably going to be something like this. That's a pain in the butt. Right. H goes on whatever, but basically attached to an N there. Those two are going to have a chemical shift in that environment. Attached to that N, we're talking probably an amine or maybe even a substituted amine. You don't get carbon, nitrogen, you don't get amides and amines much in NMR. But if those two protons touch that carbon, touch that N, we'll have a chemical shift in that environment. Okay? So that's cool. Right, now we rub these out. So that 2 to 3 area could be all sorts of possibilities. All sorts. Once you learn how to use these, it's not a problem. Right, next. Now there's a group here, HCO. Joined to a carbon, joined to an oxygen. H, joined to a carbon, joined to a chlorine. H, joined to a carbon, joined to a bromine. That is by far the most common. Okay, now these shift up a gear between 3 and 4. You get anything between 3 and 4, it's a giveaway. Why is this the most popular one? Because of this. If you've got a molecule like this, C double bond O, some kind of ester link, you probably have H's on there, which we've dealt with. And you probably have H's on there, which we'll deal with. But this is talking about what goes on the end of the ester. This is these here, 3 to 4. So in other words, carbons here, let's say you've got, I don't know, CH2 on there. If it was a methyl, right, CH2, those two H's joined to a carbon, which is directly joined to an oxygen. H is joined to a carbon, directly joined to an oxygen, between 3 and 4. So there's quite a lot going on there. You can, when I bring this and show you a proper ester, it's going to be focusing on those. If it was a methyl group stuck on the end there, all 3 would be in that range there. We'll deal with Cl and Br at some other time because they don't often come up, but should there be that situation, that's where they'll appear in the chemical shift. Okay, but that's the key one because of this business about esters and stuff like that. Another one you rarely get, although who knows, is this. I don't think I've seen a question on this. Okay. Protons, for that is what they're called, attached directly to a carbon, which is part of a carbon-carbon double bond. Those there. All right. If you look on your chemical shift data, these are quite rare. 5 to 6. I can't recall ever seeing one in that situation. That's self-explanatory. Any protons attached to a double bond there are going to give that chemical shift. Okay. Then we come to another key one, really. I hope you can all see that. I hope it's all clear enough. There's no point me drawing that out, it's fairly obvious. Which is this. You've got to watch this. Okay, this is a good one. Often questions contain aromatic rings. Okay, now aromatic rings contain, as you well know, hidden protons, hidden hydrogens, they say. Often, depends what's attached to the ring. So on this ring we'll just attach some that's on there, right? You stick an H on there if you like. Either way, I'm referring to these protons directly attached, not that one. That one we dealt with. That one had a chemical shift if you go backwards between 2.0 to 3.0. These often get a splitting pattern. I'll come because they're close to each other. I shall come to that later. But it's a giveaway if you've got 6.0 to 8.0 in a chemical shift and probably a cluster of peaks. You've got a benzene ring in the molecule. The other clue to that is a high degree of unsaturation, like a high carbon to hydrogen ratio. Yeah, that's a clue for a benzene ring in a molecule. Okay, these clues, when we actually do examples, will make far more sense. So don't worry about them at the moment. Just suck it up, will we? All right. So nearly done. So, as I keep saying, so that one, 6 to 8, classic aromatic region of the spectrum. Okay, now C double bond O, H, two more, C double bond O, O, H, right up the far end of the chemical shift region. So these are giveaways as well. So in other words, this one here is 9.0 to 10.0, and this one is 10.0 to 12.0. Very high up. They mean this type of thing going on. So you normally get a single peak in high res NMR, because as you will see, that hydrogen is quite isolated, okay, in its I say a single peak, we'll have to look at examples, but basically anything, I say not necessarily, I say I don't want to jump ahead here. That proton, you get summits within the region 9 to 10, you pound to a penny have a proton joined to a carbon, joined to a double bond oxygen. Which is not the same as the ones I showed you earlier, where you've got a carbon with protons on it there. Those have a chemical shift. If you look back, those join to a carbon, which is then joined to a carbon double bond oxygen. Those two there have a chemical shift of between 2 to 3. They are not the same as the proton joined directly to the carbon, which is joined to a double bond oxygen, which is 9 to 10. Not the same. That H there is an OH. These protons joined to an oxygen rather than being joined to a carbon. In other words, hydroxyl type groups, alcohol type groups, they're special. Very high chemical shift, and there's something else about them which I don't want to get into now, which you can use to determine those type of protons. Okay, now that is a lot of information that I've thrown at you because I just wanted to explain what that data sheet is all about. When you use it, it'll become a lot clearer to you. So really, I'm going to finish there. The first lesson is sort of explaining the basic principles and how to use the data sheet. Next lesson, I'm going to go through how to do it. Okay, see you later, guys.